Right. So welcome everybody to the discussion panel. After this lovely musical introduction, which is also related to mathematics, I have panelists here. This is Robert McCann from the University of Toronto, Svetlana Jitormiskaya from the University of California, Berkeley, and Igor Rodnianski, who is from Princeton University. And I have certain questions which was asked to panelists, but they were asked yesterday and today, so we didn't want to give them too much time to think about it, and we don't want them to suffering thinking what they would answer and what will be their responses. But the questions were asked to them, and basically the topic which we're going to discuss was indicated, and the topic which I want to start with is the following one. That so I would say that I'm old enough and lucky to, I met few mathematicians who basically knew not everything in mathematics, but they had impression of the whole body of mathematics. And they had, although they had their well-defined subject, but they understood and they were able to talk and they were able to understand other mathematicians working in very, very different areas. I would say Jürgen Moser was one of such mathematicians, and maybe Sergei Novikov, who was mentioned today as well, and some others. So it was not extremely often to meet such people. That was not unique. I mean, they were there, and I think that now we're losing a little bit of this class of mathematicians who can appreciate the whole body of mathematics, which is one body. And it was mentioned yesterday that one of the driving forces of studying mathematics is the beauty. And the beauty of this building and interaction between different parts of mathematics and meaningful interaction, that's one of the most attractive things about it. So I want to ask our panelists what they think about this relation between broadness and view of subject as whole, and specialization in particular area. I'm not talking about what is good and what is bad. Both can be good and bad, but whether we're losing it or not, whether it's important or it's unavoidable that we're losing it, that's what kind of questions I wanted to ask. And I would ask Robert to start sharing his thoughts.
So this reminds me of a story that our colleague told me long ago. She said, you know, a bad mathematician is one without any breadth, and a bad physicist is one without any depth. So Freeman Dyson talks about birds and frogs, and you're talking about the birds. Maybe Arnold was another one that could see far, almost all of mathematics. And many of us are more frog-like in the sense that we're down in the mud working in our own area. I haven't had so many interactions with birds. It's been a long time since I had an interaction with birds. A thing that I like very much about mathematics, which is a little bit different from my experience with physics, is that, at least in my perception in physics, there are a series of major trends that have been identified by important gurus, and if you're not working on one of the major trends, it's very hard to have a career. And in mathematics, there's a lot more flexibility of, I've experienced at least, people are willing to consider almost anything. Mathematicians are working all sorts of strange corners of the subject, and a lot of mathematicians are willing to take a lot of things seriously that I think physicists would not, and somehow for me that's a virtue of mathematics. So I'm sympathetic to the frogs. It's wonderful that there are some birds out there, but I'm sympathetic to the frog side of things.
All right, Lana, what is your take on it?
Well, so it's always extremely inspirational to meet an individual who can see all of mathematics. I'm not sure why do you think this is getting lost. I see quite a few contemporaries who have this property. Terry Tao comes as one example. I think it is kind of clear from his blog that he is interested in mathematics as a whole and thinking a lot about it from this general perspective. But also, I think it's important that in many fields, the true advances come when people bring new ideas, often either from a different field or it's a newcomer bringing new ideas from a fresh perspective. And what is a fresh perspective? It's perspective of a person who just finished their studies and who still remembers a lot of other mathematics. So that's one reason why new blood is so important to advance the fields. So I think the fact that it is very important to have, I think it's absolutely okay and good for people to specialize and become for deep progress in certain areas. But while they're getting education, it's extremely important for them to get the broadest picture possible, to learn all the languages of different subjects so that they can later understand talks. So, and I see that this is sort of institutional dependent. So in some institutions, the students actually are sort of forced to learn everything. In some others, the early specialization is encouraged. And I think the latter is actually a mistake. But there are plenty of institutions where the approach is actually very strong breadth of mathematical education. And also I see conferences like this one is very important. So people who came here, not just to give their own talk, but to listen to the talks of others, right? All this audience, these are people who want to learn about math as a whole, math, what is exciting things happening in areas other than their own, right? And this is really the most important thing for this connections, most important thing that prevents math from becoming disconnected. It's actually conferences like this one and the fact that people are willing to come and listen and get even some little pieces of ideas and happenings here and there. Yeah.
Thank you. Igor?
I guess I'm not old enough to remember all this,
But you experienced enough.
You remember Terry Tapp.
but I do remember Cherry Town. Yeah, I mean, I think that to some degree I agree with Lana, but I'm not sure that this is completely lost. I think there are still people who are broad and educated and see connections between different fields of mathematics. Now, whether there are fewer such people or not, sure, I think that there are also objective reasons why this should be or is happening. In the sense that, to name one, in Stas quoted in his talk, the fact that proof is longer than 9 pages, it cannot be correct.
Sorry, your microphone's not on.
Okay. And
Is mine on?
Yes.
Okay.
Let me double check that actually. Yeah, it's green. Zero
So,
is totally green. Yeah.
Is that okay? Yeah, so, well, I mean, if that's the case, then I'm afraid that the majority of papers are incorrect. That's the reality. So, you know, we're much more specialized, the proofs are much more technical. So to actually know something about a particular field, I think has become much more difficult than before. And I think, you know, it's also true that if you sometimes talk to people who claim to be very broad, you occasionally get very impressed with their knowledge when they're talking about other fields. But then you realize that when they start talking about your field, that their knowledge is rather superficial. So maybe I'd rather not have some of the people who claim that they're very broad and they know everything about everything and they can make connections between different fields. I think it's a double-edged sword. That I think nowadays, especially, if you actually know something deeply, you have to be working in that field yourself and deeply working in that field rather than collecting some snippets from maybe conferences and then saying that you know. So there's that. Now, Lana mentioned education. I think education does play a role, and I think that's part of the system. The system forces people to specialize rather early. I think the system places a lot of demand on graduate students to have many papers published by the time they graduate, because otherwise they cannot find a job. So that really doesn't leave a lot of time to be broad.
Undergraduate.
The same, yeah, I guess now it percolated down to undergraduate students, because again, looking at the admission process in Princeton, well, ideally you should have a paper published. Even better if that paper is in the annals. So, well, yeah, I mean, true, there are exceptions like Milner, but, or Pardon, but it's hard. So it forces people to specialize pretty early on. And then their opportunity to be broad is lost.
Thank you very much. I want to kind of clarify that I'm not talking about people who claim that they're broad. I'm talking about people who are other claiming they're broad. I would never said that Jürgen Moser would say, oh, yeah, I'm so broad. So I'm talking for real people, so like Gilfant, I mean, like Arnold. Like somehow I was struggling and I want to kind of share it with others. I was preparing examples of these mathematicians, and those who came to my mind were from Russia, whom I know quite well, or from Germany, and less from the United States, and less from France, I would say. Although we have wonderful mathematicians from France and wonderful mathematicians from the United States. So maybe there is something here as well, I don't know, that broadness was more favorable, certain, and you see, from this answer, we see that some people really more sympathetic for people who really get into what they know well, and rather than going around and being broad. But I would put two things. I would say that maybe we're robbing ourselves of understanding this, maybe not even so complicated ideas, and from other areas, which is we're able to learn and to appreciate. It's one thing. And second thing that, so in principle, colloquiums were supposed to play this role. And what my observation is, colloquiums are less and less playing this role. I mean, people are less and less coming to colloquium if the talk is not in their area. And grad students very often are not coming to colloquiums. So the whole thing kind of goes, it's not completely gone in opposite direction, but it goes in that direction. And then the danger is of building something like Babylon Tower, that we start to speak different languages. And then at a certain point, we'll stop understanding each other. And then it would be a problem. So just what I'm discussing, how to avoid it, but at the same time, not to lose concrete results and concrete theorems proving there.
Let me commit an act of sacrilege. I'm actually old enough to have met Arnold. And he was a great mathematician, very broad. But I once watched a video, which was shot a long time ago. It's Arnold giving a lecture at the summer school, where he was trying to explain high school students a history of distributions. It was one of the most ridiculous and ignorant things that I've ever seen. So I think there are limits to broadness. And sometimes it's a little dangerous. So
let me interject as well. So Svetlana mentioned that there are institution-specific traditions in terms of broadness or lack of broadness, but there are also national traditions. And so you see in France, somebody mentioned France, they have these narrowly focused keeps teams that are fantastic in their own area, not interacting so much with other areas always. And I can, in Italy, I've seen this as well. They're like world leading in their own area, but they have boundaries, and not so often are they going beyond the boundaries. One part of the tradition, I mean, one of the differences, I taught math in the United States and Canada, and one of the differences in traditions that I saw when I was teaching in the US, I was at Brown, which was a liberal arts college, and the math undergraduates at Brown see less math than the math undergraduates at University of Toronto, because they have this liberal arts tradition that they have to have a very well-rounded education. When I arrived at Princeton as a graduate student, my experience was I knew more math than any of the Americans in my class in graduate school and less math than any of the Europeans. And I think that this reflects that Canada has this interpolation between the British tradition of specialization and the American tradition, if you're not at MIT or Caltech, of a broader liberal arts tradition, and both have their strengths.
So indeed, the typical American undergraduate education leads to quite much less math taken than European education. And so, and with this pressure that Igor described of getting into good graduate school, students are forced to specialize. So it's probably not unusual to see students who have never taken, to see analysis students who have never taken any algebra other than something very basic and vice versa. So, and this goes against it. On the other hand, as Rob says, it is at the expense of them taking more courses in other disciplines. And of course, if those courses, so for example, at Caltech, for example, for all students, say, taking quantum mechanics is mandatory or basic chemistry. And this actually probably is a good idea. But at most other undergraduate institutions, it seems that students basically can choose whatever courses they take, and often it doesn't really lead to a coherent education in anything. And they even advised by undergraduate advisor to keep exploring something completely irrelevant. And of course, as a result, they simply don't have time to acquire strong education in the basics of mathematics. And this is a problem. To the contrary, in the former Soviet Union, I don't know how it is currently in those countries, there was no choice in math education. Everybody was taking the same set of courses. So this breadth was kind of mandatory. This is, I guess, only a property. This can only be done in authoritarian regimes, I suppose. So maybe China has an upper hand in this right now. That's the road they would be choosing. But on the other hand, even places like Caltech have some mandatory courses. So some elements of this, I think, can be implemented. And I think this would be good in principle for the development of the field.
Thank you. So let me just move in a similar direction, but not exactly the same. But I want to say that two countries which I mentioned, like Germany and Russia, Soviet Union, it was also meaningful interaction between mathematicians and physicists in both countries. And we know it from Einstein interacting with Hilbert, and there are many examples in Soviet Union as well. And that was very rewarding for both sides. And I think, again, we're losing this thing. I mean, I don't think there is any interaction between, almost no interaction between Department of Mathematics, University of Toronto, and Department of Physics. So we hardly know each other. I think it's not unusual that young mathematicians, not young mathematicians, would say without any kind of hesitation, I don't know any physics. And in previous years, it would be a little bit, he would be slightly ashamed of that. So do you think that we should also kind of encourage mathematicians to take some physics courses to have an idea of where the problem's coming from? And because I know that this interaction is meaningful. Sometimes mathematician in my memory was coming to physicists for problems, and physical problems were motivating a lot of research. Then physicists start to come to mathematics for problems because they had crisis in physics. So it's going back and forth. But interaction is always rewarding, in my opinion. What do you think?
Well, actually, we've just had a day of mathematical physics here at the Fields Institute, and we've seen some of the spectacular interactions between mathematics and physics. Maybe the University of Toronto is anomalous. Maybe the mathematics department at University of Toronto has more interactions with the Perimeter Institute for Theoretical Physics than it happens to have with the Department of Physics at the University of Toronto. But I'm okay. After a 25-year hiatus, I'm interacting with physicists again. I also have interactions with economists. And for me, it's very exciting when I arrive at the same, I go deep into my field, I arrive at some hard problem, I discover economists have gone deep into their field and arrived at the same roadblock. And that's very satisfying because I know that the issue that needs to be overcome is not an artifact of the path that I took to get there, that somehow the fact that people coming from a different direction arrived at the same point tells me it has some, it's a little bit like the maybe this discussion about Platonism and non-Platonism yesterday. It has some reality independent of the construct within my field that led me there. So that then I'm more convinced that it's a real problem. So I think there's lots of benefit from interacting with other disciplines. I think that the relationship between mathematics and physics is a pretty mature one because it's been thriving for 150 years. I think that there are a lot of interesting problems in economics and biology that the relationship between mathematics and these other fields is not much less mature, and maybe there is more low-hanging fruit in those areas for young mathematicians and future mathematicians, and more, maybe mathematics has more to contribute to these areas where it hasn't already been heavily mathematized. But a problem with all of these areas is when you talk to an economist or you talk to physicists, they say, well, you know, we don't really need mathematicians. We'll just develop the mathematics that we need, and you know, you do your thing, and that's a frustrating reaction when you get it. That we can do the stuff we need by ourselves. We don't really need outside expertise, and it's more common than you'd expect in my
Well,
interactions.
actually, SLE, which we were heard about in the talk of Stas, and we'll hear more from Greg Lawler. That's example of the thing which was completely overseen by physicists, had no idea about it. And I mean, they were working from completely different perspective. For them, it was a great surprise.
Oh, that's great.
And so there are examples in both directions.
There are examples of great triumphs,
Yeah.
but they're, as mathematical physicists, mathematical economists, we love to shine the light on those examples, but they're rarer than one wishes.
I agree about economy and biology. I think the barrier is slightly higher to studying biology for mathematicians, but physics, they can start learning without this barrier. So it's easier in this respect, maybe, but I don't know. Lana, what do you think?
Well, Kostya, so you had picked this panel of 3 mathematical physicists, and then you ask this question.
That's why, yes, it's a fair question.
Right?
And
So,
fair remark.
of course, and you know, I think it was Arnold who said that mathematics is a part of mathematical physics, right? So, yeah, of course, it's great to talk to physicists, and actually, my experience is different. I am now in some joint project on marine materials with some physicists, including a prominent physicist, Alan MacDonald, and they want mathematicians, but they really want things, they want ideas from mathematicians. It's actually very exciting. But yeah, of course, we need to talk to physicists, and yes, everybody should do like Caltech does and make everyone learn quantum mechanics. It's my conviction.
You're going to implement this at Berkeley.
Igor,
But Caltech is an authoritarian state, and Berkeley isn't.
your take on quantum mechanics.
My take on quantum. So I don't think University of Toronto is an exception. I think that this interaction is non-existent. I don't know if it's a good thing or a bad thing. I think it's just a thing. Okay, I have an exposure to a particular type of, let's say, physics, high energy physics, and I don't think high energy physicists need us. I don't think we need them all that much. Maybe occasionally to prove them wrong, or not even occasionally because they're quite wrong.
How do they react to that?
Well, that's the reason. That's one of the reasons why this interaction is not particularly fruitful, because there is no way of convincing them that they're wrong. They always have, they have moving targets, so you can pin them down. I can give you examples. Yeah. So in my talk, I didn't get to the end of the slides where I have a slide with a question of what does it have to do with ADS-CFT, and the answer is nothing. And it doesn't bother physicists that it has nothing to do, that ADS-CFT is somewhat misconceived, at least at the breadth that they were hoping for. And there is a mathematical proof now to that extent, then it doesn't bother high energy physicists that, okay, well, that doesn't matter. So that being said, I think that people who, let's say, students who want to pursue mathematical physics should take courses in the physics department to develop intuition. I think physics is extremely important, at least that's my opinion, is extremely important for developing mathematical intuition. Now, on the other hand, if you want to do number theory or algebraic geometry of a certain kind, let's say certain kind, then why should we force students to take quantum mechanics? I don't see the point. I mean, maybe they should be better served taking European history. I don't think, I'm not very dogmatic about this issue. I think it's helpful for some people, it's not helpful for others.
Well, algebraic geometry is so intertwined with string theory.
I said
and-
certain kind.
Yeah,
I
okay.
said certain kind. For instance, if you do, if you're interested in the minimal modal problem, then I think you can live without string theory.
But if you're a number theorist interested in the Riemann hypothesis, you might really benefit from
That's
some
true.
physics.
That is true, but you might also benefit from other things. Take in economics, for instance, or biology, or history, or music.
Thank you. Actually, Riemann hypothesis is related to physics and to random matrices and to everything in a meaningful way. We just don't understand it quite well. But let me ask you another thing, related, but we kind of touched a little bit. So the great Russian mathematician Sergei Novikov, who was mentioning so by me and not only by me today, I was talking to him many years ago as a young man. And he told me that we were just chatting about mathematics, and he said that actually this huge body of mathematics, if you start to think about fundamental ideas, there are very few. I mean, it is the whole building is built upon certain number and countable and kind of easily countable number of fundamental ideas. And for me, it was very interesting thought. I never thought about it. And the older I am, the more I agree with this, I would say. And so would you agree with this? And that also brings us to the fact that it's possible to have say some idea about these fundamental ideas and to kind of enrich yourself with this knowledge. And do you agree with this, or you think it is actually some kind of just beautiful phrase?
Well, I actually, one of the things that I appreciate about mathematics is somebody mentioned, I think it was Ulrika mentioned yesterday, the shelf life, that it has a long shelf life. And so that these same fundamental ideas prove useful over and over again, often in different guises in different fields. That's one of the things that excites me about mathematics. And when I was in high school, I learned to program a computer. I had I had a Commodore 64 at that time, which is now archaic, but I knew the machine inside out. I knew if the machine hung, I knew which two pins on the back of it to put a paper clip to in order to force it to do a soft reset where I could recover my data, get it unhung. Then I went to university and I started in engineering at Queen's at the other end of Lake Ontario. That was the first year that the Faculty of Engineering at Queen's required all of its students to buy a PC-compatible machine with a package of software that they were offering. And within a year or two, the Commodore 64, all the information I knew about it was obsolete. And I sort of swore never again, that I never wanted to make this investment to learn all this information that was going to suddenly become obsolete on me. And so somehow that drove me into mathematics and away from some other areas where it seemed like what did somebody say, that the shelf life of a physics paper is a couple of years and probably a biology paper even shorter, that some of the knowledge keeps changing. When we were young, we weren't supposed to eat fats. Now we're supposed to eat fats, but not sugar. Somehow that temporality really bothered me. And this idea that there are a finite collection of fundamental ideas that have permanent value is one of the legacies that I see of mathematics. Another legacy is the method of proof by which we establish the correctness or the truth of a mathematical result, which is kind of different from other. So in mathematics, we do logical deduction, whereas in other sciences, they do induction from examples. And I think this logical deduction is a wonderful sort of BS detector in this age of, misinformation and subjective truths and so on. I think it's wonderful that we have a discipline where we can all agree on what constitutes a proof, what's true, what's not true, what constitutes a counterexample. I think in this way, mathematics can be a shining light and beacon for other disciplines.
Thank you.
Okay, so there are two parts to this statement about this finitely many ideas. So you took the approach that this is important, that there exist ideas that have this very, very long, maybe infinite shelf value. And of course, this is extremely important. But if there were truly finitely many of them, as you say, and like, well, finitely in this finitary logic, not sense, right, clearly finitely, then our trade would have been doomed like in a few years, right? With all these machine learning advances, if everything it just can be boiled down to these finitely many ideas, we can teach computers to do what we do, right? I think the whole point is for the humanity to kind of keep adding to this collection of big ideas that become permanent knowledge. And this happens slowly, but slowly, again, depending on the definition of permanent and universal. So whatever we learn now as undergrads or even in high school, this used to be new ideas at the time of Newton. And I bet that these new ideas, they started with new ideas for something very concrete, and then it was realized that it is a lot more universal, and such realizations for some ideas came very, very slowly. It may have taken even centuries, right? And so whatever we do is producing new ideas with the hope that they will become fundamental and universal, maybe at some scale, right? So this is some trees, this is a fractal, right? So there are certain roots, but I reject the statement that there are only finitely many and one cannot add to it. The whole point
No,
is
you
to
can
add
add,
to it.
of course, that's
Yeah.
most valuable to add to this.
Yeah, but then there are next level fundamental ideas, and of course the whole point is to create these fundamental ideas with long shelf life and that be good at a certain level, which can with time turn out to be even more fundamental than one ever expected.
I think it's a beautiful phrase. Maybe at some meta level, it's true, but so there is another way maybe to express that, which is to say that everybody cooks with water. Nothing else has been invented at the end of the day. But like Lana said, okay, you start with water, but then you can add different ingredients and spices. Is it less fundamental than water? Maybe, but so what?
Okay, I see this. I hear. I mean, it's interesting that I didn't expect anything like one stream of enthusiasm about anything we're discussing. And the spectrum of opinion is important, I think. And that reflects really the spectrum of how people do mathematics and how people approach mathematics. And we're all different personalities, individualities, and that's valuable. It's the discussion of this type, I think, they also important, maybe. So let me ask another question, which is also related, maybe less, to what we discussed before. So we're celebrating this 100th anniversary of the Congress, and in connection with this idea of having Fields Medals, which played important role in development of mathematics. This is a topic which can be discussed as well. The role it played, positive, negative, whatever. But I want to discuss something which happened 25 years before that. That is the turn of the 19th, 20th century, when Hilbert famously formulated 23 problems, which will, I don't think all of us can formulate all 23 problems, but at least all of us heard about them. And I personally think that it was a very eclectic collection of problems and kind of ad hoc, and a collection of something. One of the problems was there's full set of axioms for physics. And that sounds to me a little bit far-reaching. But anyway, this was important thing and played a role in the development of mathematics. Now, Hilbert was probably one of the people we was talking before who kind of had the picture about the whole mathematics. But then when we were turning 20th century, it were attempts of this type, several set of problems. And I don't think 25 years later that they played any role in what people kind of, they were formulated and people kind of happily forgot about them. And I don't think they're playing any role. So why is this happening? Why Hilbert problems were so well received and kind of served as a push for development mathematics, and what we did in 21st. I don't want to name names of this collection, but there were several more less useful or less appreciated.
Maybe someone else wants to go first.
Yes, why would we change the order?
Well, maybe just to clarify, maybe some of these collections that you were not willing to name, I can think of the clay millennium problems. I would say that they were influential. I mean, they were already, by the time they were formulated, I think they were widely recognized as being important problems. Maybe formulating them was codifying their importance and also attaching monetary value to them, which was not insignificant at the time, maybe a little less with inflation now. One of them has been solved. We know that. I think, okay, I can't speak about other problems, but for instance, the Navier-Stokes problem, I think there was a lot of interest to it, and it certainly intensified after the formulation of this problem. Now, I agree that they certainly did not have the same influence as the Hilbert problems. However, you know, I can't say what the landscape looked like 25 years after Hilbert formulated them. Maybe nobody cared. I don't know enough history, I suppose, to make the judgment.
No, people cared about them. Even now they care
Even
about
now.
them.
Well, now they care about it more than perhaps 25 years. You know, if let's say millennium problems are not solved in another 75 years, I think people will care about them very much. That being said, okay, so maybe there are many different questions hidden here. One of them is,
do we need this collection?
exactly. So does it benefit mathematics to have a collection of good open problems? I think the answer is absolutely yes. I think it's healthy if they come from different sources because, well, there was one Hilbert, and it's maybe best if these open problems are not monopolized by one person who then dictates the direction of a particular field, or as it actually happens in some of the fields. And now I'm going to borrow a book, a page from your book, and I'm not going to name. But certainly, I mean, there are certain fields that are completely driven by a vision of, let's say, one person and have a collection of open problems that everybody is supposed to solve. And maybe that's not entirely healthy. But nonetheless, having these problems is extremely good. So the answer to that question unequivocally for me, yes. It's very important to have a collection of open problems.
Yeah, I agree with the letter that it's extremely important. So I am in one of such fields which was hugely driven by open problems by Barry Simon. I also know that in topology, the list of problems by Rob Kirby have been extremely influential. But speaking of Hilbert, again, Arnold comes to mind, and I remember him saying that Hilbert's problems were definitely like had a fraction of influence of what Poincaré proposed at about the same time, which actually predicted, I don't quite remember, but definitely he predicted the quantum mechanics, right? Kind of, he predicted general relativity. So there were some papers that had very little, there were three things, I don't remember what is the third, but that there was, it didn't have as much PR as Hilbert's problems at the time, but if you think about what these two people actually said at the turn of the century of how mathematics would be developed, so Poincaré predicted the really important things, even though he didn't quite formulate it as a list of problems. So, but yes, this is a competition of visions of two giants, and one may have a better vision than another. But in any case, Hilbert's list of problems was influential at the end, although indeed it is not clear to us whether the framework of 25 years was sufficient to see the influence. I think when we're so when were the first problems solved? Hilbert problems?
Perelman?
No,
No,
Hilbert
just- no,
problems.
no.
Hilbert,
problems.
2 years after.
Okay, maybe
Guinea solved it 2 years after.
some were solved
It was pretty
soon,
simple problem.
but there were many that were solved many years later, right? In the 60s
Well, they're
and the
unsolved.
70s. Some are
16
not
is
solved
unsolved.
yet, right? So basically, and again, it is important whether a problem was just solved or whether it's really started a big new thing, right? So.
Arnold, by the way,
Arnold solved some, and it's particularly striking that he would say that his he was really fond of Poincaré. Anyway, so I think a list of problems are extremely important, but also predictions by the visionaries. So there are few real visionaries among us, and whatever predictions they make, it's important to listen to them.
Well, I guess it's great if you can be a visionary.
Yeah.
And I'm willing to believe that these lists of problems are important, and they probably play a more important role for some mathematicians than for others. I mean, there are mathematicians who are great problem solvers, and some of them won Fields medals. Again, it's an example. You can probably think of others. There are other mathematicians who are theory builders. And on my own experience with mathematics is that I'm terrible at thinking about other people's problems. I'm only really motivated to think about problems that I formulate myself. And somehow I think the ability to formulate these problems comes from this broad exposure to other disciplines and maybe different areas within mathematics that we were talking about earlier. So they haven't played a big role in my mathematical life. It would be somehow it would be good luck for me if I happened to do something that contributed to the solution of one of these problems, but it wouldn't be probably the initial motivation for me. But I'm sure there are people for whom it's a very strong motivation. So I think the richness of different approaches to mathematics and different mathematical personalities leave a lot of room for these problems to have a great beneficial influence, and in some cases, and less beneficial in others.
So, thank you all. And before I think that we didn't do last time because it was not enough time. We didn't ask audience about their opinion if some people want to say something, and I want to give this opportunity to people. So if somebody wants to reflect on something we discussed today, please go ahead and
Or questions.
share your views
Or questions. Do they have questions?
or ask questions to the panelists. Yes, Kumar.
So in terms of the way you were discussing the first question you asked about the breadth of ideas, there's a whole spectrum of engagement with mathematics. You were mainly focusing on the education part. But education, the way we learn mathematics doesn't end once we graduate. We spend our whole life learning mathematics. And so I wonder if you could say, what's the opportunity for places like the Fields Institute to do, this kind of meeting there, to bringing together people from fields, and with eager to learn, with eager to listen to these different things that are outside of our field. Maybe that's a special role that places like that could play that is not captured so easily within established institutions like a university, the silo structure of departments. Speak a little bit more to that. I mean, what can institutes do to encourage this culture of being deep in your field, but also being open to listen to what other people are saying?
That's a question to you guys.
So one of the things that the Mathematical Sciences Research Institute at Berkeley does that I really like is they tend to run 2 different programs in parallel, but they try to choose programs that have some relation to each other in the hopes that there'll be cross-fertilization.
Well, I agree with your point. I mean, I think that institute like Newton Institute, Field Institute. They might play very interesting role. It's not an easy task, no. It was many attempts to bring people from different disciplines, and this repulsion, kind of natural repulsion, very often kind of take over and you don't achieve this goal.
Fields has actually been pretty successful in my experience at attracting participation from people from different disciplines.
So maybe Misha?
Sure. It is also concerned with the first topic that we discussed about sort of breadth in mathematics, importance of breadth and connections with different fields, and I came from the same culture. Of course, the breadth advanced to nice school. People believe that the most important ideas in mathematics
Misha.
come actually from interaction between different fields, and we just heard here about Langland's program. So what could be a better example of how so ideas from different fields, when they merge, can lead to something incredibly deep, so in mathematics. And there would be no way, if some people focus completely on representation theory or completely on number theory, no way that anything like that would be possible. Or we all know about Witten's contribution, physicists, Witten's contribution to mathematics, incredible. Mathematicians would not be able to do anything like that. So his kind of vision of physical ideas and interest in mathematics, so they led to this. But let me tell you a little anecdote just from my experience. So just a joke. It is from long ago, from the beginning of 90s, we had some faculty meeting in Stony Brook, and there was a discussion of some applications in PDE. And one of my colleagues said, well, PDE is a boring field, all this a priori bounds, etc. Nothing like Poincare conjecture is there. And we know the story of Poincare conjecture. So, so merge of two fields led to deepest sort of discoveries and achievements in mathematics. I firmly believe of that, and I think that there are old examples, there are new examples, and there will be plenty of future examples of this kind. And I think that we should strive for understanding different fields, connecting them, and to teach our students not just to focus so on the topic of the thesis and just to not to see anything else. So,
Thank you. Somebody else?
Maybe a couple of comments. One of them is very local because we were discussing in Gelfand, Novikov. There was something very special in the Soviet Union that probably people who never lived there do not realize. There was nothing else to do there. At the age of 13, I wanted to go to humanities. At 15, I understood that there were no humanities in the Soviet Union. Equally, there was no genetics, so nothing but physics and mathematics. So that, and technically maybe 1.5 city, correct? So everything was very concentrated and best minds worked on mathematics. The second thing, we discussed a lot interdisciplinary things. They do exist, but usually it means that physicists and mathematicians do in biology. It's not that they in between. In about 2010, we had 3 biological institutes in our Department of Biology. All of them were led by people who were trained in physics. Stu Kaufman, Maya Pachushki from MIT, and I forgot the third name. So if you see advance, it's physicists doing something in biology, mostly, I don't know, mathematicians sometimes, but it's usually physicists changing the. This is how it works, and my colleagues worked on neural networks. Her PhD student is in Brain Institute in the Faculty of Medicine. So this is how we do interdisciplinary research now.
Well, yeah, thank
I want to
you.
give a quick answer to Kumar's question.
Sure.
She doesn't mean that she's
I
Oh,
have-
yeah.
So for most people, their learning stops at the undergraduate, early graduate level. So kind of the best of us keep learning, right? But it is hard to keep learning later. And probably the easiest way to learn is to actually get exposed and to get curious about learning something is to listen to great talks, to great expository talks on something exciting. And that is the role of Fields Institute. So I think if the talks are preserved for viewing by the public, that is very important. So for example, I happen to know that Bourgain used to watch this videotaped talks of great recent discoveries a lot, and I'm pretty sure that it kind of fed his greatness. So once this became available, so I think that's one role to kind of create opportunities for more really accessible talks on the hottest development. It is not always that people who do great things that they can give great talks, but whenever there is some intersection, this is something that Fields Institute can step in.
We do archive all our talks, they're all available, but maybe we need to do more curation.
Maybe, can people comment on the talks? That's a natural way to curate, right? Or give, ratings or something like that.
That's also a way to discourage people from giving them.
Yes, better not.
Well, we're coming close to the end of our discussion session. Let me kind of as a remark at the end say that let me reconcile, try to reconcile Poincaré and Hilbert. I agree that open problems are important, and it's important for younger people to establish themselves and to prove themselves, but also important when people formulate programs and vision and program which should be developed, and that maybe to next generation or after that. So both are important, and maybe that's what we need when we'll be finishing 21st century and going to 22nd, to have kind of list of programs needed for mathematics to develop, like Langlands program, which we were discussing before, was extremely influential in many fields. So maybe both things are needed, and should be encouraged for kind of experts and visionaries to produce for the whole of the subject. Well, if somebody wants to say something, it's time to do it. But otherwise,
So looking out from the stage here, I just want to point out this interdisciplinary collaboration at the back of the room. So an architecture student here at University of Toronto designed this back wall, which it looks a bit like the darts and kites tiling. I think it's an aperiodic tiling, but moreover, it's providing sound absorption for the room. So it's improved the acoustics here.
beautiful.
So it is aperiodic.
I think so, yeah.
The acoustics has measurably improved.
Well, thank you, everybody. Thank you.